Welcome. We're going to take a look at our second function that we're doing our JTBs on, just the basics quizzes, and ultimately we're going to be coming up with all of these solutions, and we really need to be dead on these. So let's go ahead and get started. We know that we would like to find the first and second derivative, and we got a little bit of work to do to come up with those. So first derivative, I have a product rule. I have this function of x times this function of x. So I want the first function as it exists, negative 4x, times the derivative of this function, which is a chain rule involving e. The derivative of e to the is e to the, leave the inside function or the baby function 3x alone, and then treat the baby function, the derivative of 3x is 3. So that's the plain old first times the derivative of second plus the derivative of the first, negative 4, is the derivative of negative 4x times the plain old second. And I'm going to just clean that up a little bit. Negative 12x e to the 3x minus 4e to the 3x, which is great. We're going to set that thing equal to 0 then. So we got our first derivative. Let's go ahead and record it. That's negative 12x e to the 3x minus 4e to the 3x. Or we could record it in factored form as well, which I'm going to do next. To solve this, tempting to just divide both sides by negative 4, divide both sides by e to the 3x. But I'm going to group and factor. So I can factor out a negative 4. We can't factor out an x, but we can factor out an e to the 3x. And that leaves us from this term a factor of 3, a factor of x, and from the second term just a factor of plus 1. Check that with distribution. I want to know when that equals 0. Because I'm going to use that to find out possible locations for maximums and or minimums. So a number times a number times a number equals 0 only when one of those numbers is 0, and negative 4 is not 0. And e to the 3x, a positive number to a power, or for that matter, a negative number to a power, anything other than 0 to a power cannot be 0. So this just becomes, when is 3x plus 1 equals 0? That is when x equals negative 1/3. So at that point I'm thinking, if there is a maximum or minimum, it is located x equals negative 1/3, because that is where the graph levels off. So in my head, what I'm thinking is, on a graph, and I have no idea where it is at this time. Let's say so negative 1/3 here. Let's say negative 1/3. I could put that value in here and see where it is, but let's say it's down here. I believe it's going to be negative. The slope levels there for a minute. So maybe my graph comes down and touches, and we have a minimum point. Maybe it comes up, touches, and we have a maximum point. But it's possible it might come up, level off for an instant, and then head up. And we don't have either, so we need more exploration. But that's a candidate for max or min. Okay. Let's find second derivative. In fact, I'm just going to put here max min, so we can come back to that. For the second derivative, I'm going to build the second derivative off of this. You could certainly build it off of this as well and have an extra product rule in there, but I'm going to go term by term through here. So the derivative of this first function, once again, we have a function of x times a function of x. So I need the plain old first function, negative 12x, times the derivative of the second. Derivative of e to the is e to the. Leave the baby function alone, and then treat the baby function. So it's the outside derivative, e to the, of the inside function, 3x, times the inside derivative, 3. So that is just plain old first times derivative of second plus derivative of first, negative 12, plain old second. And then I still need the derivative of this. But the derivative of this is just negative 4 times the derivative of e to the 3x. Derivative of e to the is e to the. Leave the inside function or the baby function alone. Treat the baby function. And let's clean that up. Negative 36x e to the 3x minus 12 e to the 3x minus another 12 e to the 3x, giving us negative 36x e to the 3x minus 24 of those e to the 3x's. So likewise, what we did earlier, let's go ahead and factor that. I can factor out a negative 12. I get, and hang on a second, I can factor out a negative 12. I can also factor out an e to the 3x. Divide by negative 12, I get positive 3, and I still have an x here. Divide by negative 12, I get positive 2, and the e to the 3x is gone. And that, when that is 0, we might have we would have an inflection point. So when is negative 12 0? Never. When is e to the 3x 0? Never. When is 3x plus 2 equal to 0? When x equals negative 2/3, which would be an indication we have an inflection point at x equals negative 2/3. So second derivative, I'm going to jot it down here. I think I'll jot it down in this form. Negative 36x e to the 3x minus 24 e to the 3x. Of course, you could jot those down in their factored forms as well. Okay, now let's talk about the graph. If I have a function I'm not familiar with, namely this one, three things I'll typically try to do. If convenient, I'm going to put a 0 in and try to figure out where the graph is on the y-axis. And I put 0 in for x and I get 0 times the rest of this, I get 0. So there's a nice convenient point. And then I'm going to put a big X in. And by a big X, I mean maybe 100, 1,000, 1,000,000. But even for this function, even 10 works. If I just put in 10, I get y equals negative 40 e to the 40th. E to the 40th is an enormous number. Negative 40 times it makes it a more enormous negative number. This graph is going to go down. Now, if I put in negative 10, I get positive 40 e to the, oops, this should have been a 30, I'm sorry. You probably knew that when I put in 10. I get e to the negative 30 if I put in negative 10. And that's equal to 40, which is fairly significant at times, but not when it's divided by e to the 30th. E to the 30th, you can go ahead and check, but I suspect that's many, many millions. Probably not a billion, but many, many millions, perhaps a billion. Anyway, we've got a positive divided by a huge, huge, huge positive when we put in a value out here to the left 10, which implies that we're positive divided by positive, but very close to 0 and getting closer to 0. I think the shape of the graph as it's heading out this way looks like that. Okay, let's put this together with what we've learned about inflection point and, more importantly right now, max min. I've got a minimum at negative 1/3. Well, that means I've got a relative max or min at negative 1/3. So that means the graph levels off here. And if it levels off, if it's doing this right now, it must come up and level off somewhere up above the x-axis and head down. How high is that? I don't know. If we wanted to know how high it is, we could put negative 1/3 into the original function, calculate that out. Now, I have an inflection point at negative 2/3. Right now, we're getting sucked into this x-axis. We're cupping up. But notice at some point, I've got to start changing and cupping back down. And I'm kind of overemphasizing that, but that happens at negative 2/3. Oh, we got a whole lot of what we need right here. Okay, so the maximum x, we do have a maximum. It occurs at x equals negative 1/3. This graph is going to approach 0, but it's never going to get there, so we can't say that it has a minimum. It keeps getting closer and closer to 0. It goes down forever, so we don't have a relative minimum value. I mean, you could say it's approaching negative infinity, but we're looking for relative minimums, relative maximums, so there is none. No relative minimum. Point of inflection we learned was x is negative 2/3. When is the function increasing? The function's increasing as it's going up from negative infinity to negative 1/3. It's not increasing at negative 1/3. Let's get everything into focus here. Can we do that? Okay. So it's not increasing at negative 1/3, but it's increasing until we get there. It's decreasing from negative 1/3 on. When does it concave up? From negative infinity over until we get to the inflection point, negative 2/3. That's when it's cupping up. When is it cupping down? Starts right here and begins its deceleration process. So that is negative 2/3 to infinity. Now, for the sign charts, this can be really helpful. Let's say we're not completely comfortable going through the graphing method the way I did with the big X, the big negative X, the 0. Once we get to these points right here, let's say we can just mechanically, we're great at going through the mechanics and coming up with the inflection point and the max min. What we can do is we can go to our sign chart. So let's say we can't even see the graph, we don't know any of this information yet. For my sign chart, y prime is 0 only at negative 1/3. Now watch this. If I pick a value bigger than negative 1/3, let's just say arbitrarily I'm going to put in 2. If I come back up here and put in 2, look what we get. I get negative 4 times positive number here times a positive. I get a negative times positive when x is 2. And negative times positive is negative. All right, how about a number less than negative 1/3? I'm going to put in, say, negative 4. Again, that's arbitrary, just something out here to the left. If I put in negative 4, this first number stays negative. The second number, e to the negative 12, is still positive. But if I put in negative 4 here, I get a negative. So it's negative times negative, positive, which means our graph goes through a phase where it goes up, maxes out at negative when x is negative 1/3, and then comes down. So this is an indication right here that we got a maximum. The graph's going up, then coming down. All right, let's do the same thing with the inflection points, or point in this case. At negative 2/3, we're at 0. Let's put a value to the right of negative 2/3. Arbitrarily, I'm going to choose 2, something out here. I get negative times positive. When x is 2, this is positive. Negative times positive, negative. Arbitrarily, I'm going to pick something to the left of negative 2/3. I'm going to say negative 2. If I put in negative 2, I get negative. This is still positive. When this is negative 2, I get negative 6 plus 2, negative 4. Negative times negative, positive. What does that mean? That means we are cupping up in this motion. We might be going down, we might be going up, but we're cupping up until we get to, take a look, back to the graph, we're cupping up until we get there, and we're going back down. We're cupping up, and eventually we're going to start cupping, not just going down, but cupping down. Now, would that be enough for us to know that that's not happening? How do we know we don't have a minimum over here? Because all we knew here was that it's cupping up. Well, this is cupping up and getting sucked into 0. But how was I to know that that happens if I don't really get that whole big negative value? Well, I didn't have another. The only place that the slope is 0 is at negative 1/3. So that can't happen. The slope can never be 0. It gets really close to 0. The slope gets really close to 0. So we could actually build all of this and this, and then try to work out the graph up here from that information. So a lot of triangulation here from the graph to this to this to that. Lots of, if I know this stuff, I'd have a pretty good feel for the graph. If I know this, I should have a pretty good feel for the graph and a pretty good feel for this. All very, very tightly intertwined, and a great tool for handling some complex functions before we've ever dealt with them. Just for the sake of it, let's go ahead and take a look at our Let's go ahead and take a look at this graph. We've got negative 4e to the, negative 4x, thank you, second e to the 3x. And I'm just going to put that in standard zoom 6. So we see, if we're looking at that shape, one thing I might want to do here to kind of emphasize that, I think I'm going to go window y min, y max. Let's just go like negative 4 to 4, or to, actually, I'm just going to go up to 2. Let's just kind of exaggerate that a little bit. See how we get sucked into that axis. And there we have a pretty decent shape. I'm going to go and look at this point right up here, that maximum. Second calc max, get to the left of it, enter, get to the right of it, enter, and when I hit enter, we should have a pretty good feel for what it's going to be. There it is. With some rounding error from our calculator, it believes it's basically at negative 1/3. If you wanted to see where the inflection point is, we could do second trace value. I'm going to go 2 divided by 3, except that needs to be negative. Negative 2 divided by 3. It looks like the inflection point just there a little bit to the left. So we pretty well nailed it here. I could certainly stretch that graph out. Let's go, say, negative 4 to just 2. And it's going to start to appear more like our curve at that point. Okay. And we can somewhere along the line kind of visualize where this is going, cupping up, cupping down. Okay, so there's a lot going on there. I would say pretty challenging to get this one right on the first try, but I know we'll have some people that do it. And good luck to you. Let me know if I can help.